Hello everyone, welcome back. In this video, we'll be discussing about the first and the third problem of today's weekly contest, final array state after k multiplication operations 1 and final array state after k multiplication operations 2. Both the problems are exactly equal, the only difference lies in the constraint, and because of the constraint, the second problem, the value of each element you need to return can be very huge, and hence they ask us to return 10 power 9 modulus 10 power 9 plus 7, which is not there in the first problem because the value would not be very huge. So as always, we'll start from the very brute force solution, which would be sufficient for the first problem itself, and then we'll see how to optimize it step by step to fit it with the constraint of the third problem. So let's get started. The problem states that you're given an integer array nums, an integer k, and an integer multiplier. So you need to perform k operations on the given array nums, and after you have performed all the k operations, you will apply modulus 10 power 9 plus 7 to every element of nums and return that as the answer, right? So what is the operation? Operation is you will find the minimum value x in the given array nums. If there are multiple of them, you will break the ties with the indexing and replace the selected minimum value x with x multiplied by multiplier. So you will keep on doing this for n k number of times, and whatever is the state, you will return that as the final answer. So one thing to note here is the modulus should be applied towards the end, because if you apply modulus along with the operation, the value finding out the minimum would be difficult. Basically, you will not, the actual minimum in the array can be something else, but because you applied modulus, you are not able to identify that. So the modulus should be applied in such a fashion that it should not interfere with the minimum value. So you can't simply keep on taking modulus along with the operation itself. So something you keep in mind. So let's take an example. Let's say nums is 2 1 3 5 6, k is 5, multiplier is 2. So we need to apply the operation 5 number of times, and the value of multiplier here is 2. So let's apply the operation. We'll first find the minimum value here. Minimum value is 5. Minimum value is 1. So we'll simply multiply it with the multiplier, which is 2. So the array would become 2 2 3 5 6. Now again, let's apply the second operation. What is the minimum value? Minimum value is 2. So there are two 2's. Which of them will we pick? The one which occurs first. So in this case, this one. So we'll simply pick this and multiply it with the multiplier, which make it 4. Now after that, we'll apply the operation here. Again, pick the minimum value, which is 2, multiplied by 2, which will make it 4. Now on this one, again, the smallest is 3, multiplied by 2, it will become 6. And finally, on this one, the smallest is 4. There are two 4's, which will pick the first one and multiply it by 2, and it will become 8 4 6 5 6. So after applying 5 operation, this is the state, and because none of them is greater than 10 power 9 plus 7, after applying modulus, it will remain 8 4 6 5 6, and that is our answer. So hope the problem statement is clear. Now what's the brute force way to solve this? The brute force way would be like just simulate whatever is given to you. So you have been said that okay, you need to apply 5 operations. So just apply the 5 operation in the given fashion. So in this scenario, we'll pick the minimum value. Minimum element is 2, right? And you will simply multiply it by 4. So that's the end of one operation. Now you will apply the same thing again on this array, and so on and so forth until k number of times. So what's the complexity of this entire brute force solution? You are doing something k number of times, right? Now each time, what you're doing, you are picking the minimum element and then multiplying it by 2. So finding out the minimum element in this array, if you do it naively, it can take you order and time. You will simply iterate over the entire array and figure out the one which is the minimum value. So if you do it naively, this entire algorithm would take you order k into n time, which is sufficient for the first problem because the value of k here is 10 and the value of n here is 100. So it's sufficient to just do this k into l algorithm for the first problem. But definitely will not work for the third one because the value of k is very huge and the value of n is also larger than the previous one. So there are two things, right? The value of k is very huge, 10 power 9, right? And the value of n is 10 power 4. So there are some ways in which you can optimize this n for sure, right? Like you are doing a linear iteration to find the minimum value. There are better ways to do it using some sorted data structures. But even though you optimize this, it will not be of much value because the main culprit here is k. K is very huge, 10 power 9. So you can't afford k. What does it mean? It means that you can't simply keep on applying the operation one by one. You need to somehow figure out a way to group the operation and apply them as a whole, right? Because if you keep on applying this operation one by one, you will take 10 power 9 iteration, and even if you do order one things in each iteration, this algorithm will not be sufficient. So grouping certain operations, what does it mean? It means that you need to somehow know, okay, on this index I will multiply this multiplier x number of times or exponent number of times. On this one I will apply the multiplier x2 number of times, and so on and so forth. So this problem in general is looking hard. So whenever you face this kind of issues, try to either reduce the number of variables you have or try to solve the same problem on a smaller array itself. So basically try to reduce the problem and solve the smaller version first before jumping to the original problem itself. So let's do the same. In this scenario, there are not much variables, so we'll try to reduce the array size itself. We'll simply say we'll first solve the same problem on an array size of 2. And if we are able to do so, we'll try with 3, and then we'll see if we can generalize whatever solution we have so far. So we need to solve the same problem on this 2 element array, and let's assume that m is 2 and k is 100, right? So we need to come up with some sort of algorithm wherein k is not there in the time complexity at all. That's our goal. So if you haven't tried this version of the problem yet, this is the right time to pause and try to give it a try to solve the problem for this 2 element version by yourself. So hope you at least tried by once. The main thing to notice here is, let's say you apply the operation here, so this will become 8 and this will become 7. Now the smallest element would become 7, so you will apply the operation on this element now. So basically this will become 14 and this will remain 8. Now this will become the smallest element, so you will apply the operation here, this will become 16, this will become 14. Now you will apply the operation here, this will become 28, this will remain 16, and so on and so forth. So what you see, what's happening, you are simply applying the operation on every element in every alternate turns. So in other words, you are applying k by 2 operations here and k by 2 operations here, and then whatever is remaining you will apply starting from here, because this is the smallest element which you have started with, right? Now why is this the case? Like will this sequence exist forever? That's the first question. Second, will this always be the case that you will apply operation, like once you apply the operation on the first element, you will have to apply the operation on the second element, because now second element is become greater. So the answer for second question is simply false, because you can see even in this small example, if you apply the operation on the first element, this will become 2 and 7, and after this you will not apply the operation on 7, rather you will again apply the operation on 2 itself, because 2 is still the smaller element, right? So we'll come to the second question and deep dive there once, but let's first answer the first question, wherein if this is happening once, will it happen forever or not? So in this scenario, answer is yes. Why? Because you notice you are saying that there is some element, let's say x1, and you are multiplying it with m, and this is becoming greater than the second element, which is x2, right? Now this inequality is there. Now let's say you apply, because x1 was smaller than x2, as in like x1 here is 4 and x2 here is 7, so let's say this x1 is smaller, so you apply the operation on x1, this becomes something like this. In other words, your array is now m multiplied by x1 and x2. And because this inequality is satisfied, that's something you are assuming, you will now apply the operation on x2. So basically you multiply 7 by 2, which is 8 comma 14, which make it 8 comma 14. Basically what you have now is mx1 and mx2, right? Now which of these two will be smaller? The answer is surely mx1. Why? Because x1 itself was smaller than x2 in the very first case itself, because that's why you applied the operation on x1, right? So we know that 4 was smaller than 7, and hence mx1 would be smaller than mx2 itself. In other words, you will now be applying operation here. So if you apply the operation here, what would this now become? This would become m square x1 and mx2, right? Now the question really you need to answer is that if you keep on doing this, currently you can see this, okay, 16 is smaller than greater than 14, so you will now apply operation here, but will this always continue? In other words, would mx2 be smaller than m square x1 always or not? The answer is yes, because this inequality was true. Like, because you had said that you will apply the operation on this element now because of this inequality. This inequality will also be true. Basically you simply multiply m both the sides and you will get with this exact inequality. And because of this, you know that this one will be smaller and you will be multiplying m to this one now. And once you multiply m to this one, again both x1 and x2 are multiplied by m square. So whichever was smaller initially would be smaller now, and you will simply apply the operation on that one again. So you will simply apply operation on x1 now, and after this point, again with the help of this inequality, you can simply multiply m here. You can see that m cube x1 will be greater than m square x2, which means that you will now apply operation here. That is, you will make this m cube x2, right? Basically you are simply alternating from this point onwards. So what we just proved is, if this inequality is true, that is, if after applying one operation this becomes greater than the previous one, the largest one that exists, we are sure that we will simply be alternating the operations one by one. If this is not clear, rewind the past 30 seconds and you will be able to understand this with if it's still not clear, I would encourage you to try it on a pen and paper, and I'm very sure you will get it. So what we just proved is, if this inequality happens between these two elements, I know how to solve. I can simply divide my operation half and half, and whatever is remaining I will start from the first element itself. So in this scenario, let's say if k is 101, instead you will apply 50 operations here, and what if, like, the one which is remaining you will apply here, because this one was the smaller one, right? So overall at the end your final values would become 4 multiplied by 2 power 51 and 7 multiplied by 2 power 50. So this will be your final array after this key operations, right? Now what is the overall time complexity now? First thing, you checked whether this inequality is true or not. If this is true, you simply divide it half and half, and whatever is remaining you will give it to the smaller one. So this operation of dividing things is simply order 1, and figuring out 2 power 50 and 2 power 51 here can, or rather 2 power k by 2 in very brute way, can be done in log k time using fast exponentiation. So if you don't know about fast exponentiation, don't worry about it. Basically it's a way to find out a power b in log b time instead of order b time. So we'll discuss that somewhere in the end. But overall, this operation will take log k. This operation will take log k time, and the other operations are always are anyways order 1. So overall complexity is now ordered log k. So we successfully removed k from the time complexity. We introduced log k, but log k is a lot smaller than k itself. Now, this all things were true when the inequality that m x1 is greater than x2 was true. But if this inequality is not true, this will will this entire approach work or not? The answer is yes, it will work, but with some more things in place. So would encourage you to pause and try to solve the same on this example, and I'm very sure you will be able to solve it if you have focused in the previous part. So the solution is straightforward. Let's say we apply the operation here. This becomes 2,7. Now, first of all, this doesn't satisfy this criteria, because if you do m cross x1, x1 here is 1, so m cross x1 would become 2, and x2 is 7, so 2 is not greater than 7, right? So because this inequality is not satisfied, you know that this alternate approach would not work here. Now, let's say you apply the operation here, 2,7. Is the inequality satisfied? The answer is no, because m cross x1 is 4 and x2 is 7. So again, 4 is not greater than 7. And because this inequality is not satisfied, you are sure that you will be applying operation on x1 itself, right? Because if this is not satisfied, it means x1 is still smaller, right? So you will apply the operation here, and this will become now 4 and 7. Now, is this inequality satisfied now? Answer is yes. 4 cross 2 is 8. 8 is indeed greater than 7. So this inequality is now satisfied. Indeed, this entire thing has now become the previous problem itself. So basically, after applying some operation, we were able to get to a state where this inequality was satisfying. And after this state, everything would now be log k itself. So there are two questions overall at this state. So after this, we know how to solve. Now the two questions that we have is it always feasible to reach this state? First. Second, how many operations will be there to reach this state? Because if the number of operations to reach this state will be of the order of k, or like k by 2 or something, again, this entire approach would not work, right? So two questions. So let's answer the second question first. Let's say it is possible to reach this state for sure. How? We'll answer it in a moment. But if it is possible to reach this state, how many operations will be required to reach this state? The answer is only log k operations. Why? Because, or rather log x operation, where x is the value of the larger element. Because what you are doing, you are simply applying the operations or multiplying m to the smaller element continuously, and because you are multiplying, everything is growing exponentially. So some element was x1, it become mx1, then it become m square x1, m cube x1, and so on and so forth. So just think about it. This, if m is even 2, which is the smallest value of m, even in that case, in just log of x2 time, you will be able to get to x2, right? So this entire thing would be log of x. So basically you are applying the operation log x number of time, and applying the operation 1 by 1 log x number of times would be lot smaller than applying the operation k number of times 1 by 1. So this part is sorted. Now the question is it always feasible to reach this state? Because if it is not feasible to reach this state always, then this solution will not work. We need to come up with something else. So the answer again is yes, it is always feasible. Why? Because think about it. What you are saying is m cross x1 is not greater than x2. What does it mean? This means that after you multiply m with x1, the value that you will get is still smaller than x2, which in turn means that you will simply apply the operation on this m cross x1 again. So after you apply the operation again, this will become m square x1. Like this entire x1 will become m into x, and this inequality will become m square x1. Now again, if This inequality is also not satisfied. This means this is again smaller than this one, which means you will again apply the operation on the first element itself. So you are simply incrementing your first element continuously every time you are multiplying with m. So at some point, for sure, this inequality will be satisfied, because at some point this x1 would reach a certain value at which if you multiply m, this would grow above x2. So for sure this state is possible. Basically, for sure this inequality is possible, and once this inequality hits, we know that everything will become alternating. And how much time will it take to hit this inequality? Log of x, because after that you are sure that this x1 would be greater than x2 for sure. So overall, what you're doing log x operation. Each operation, if you do naively, that will take order and time, but as we discussed, we can make it log n as well if needed, with the help of some set or any ordered structures. So overall, n into log x time plus log k time, because after you did all of these, you will simply keep alternating and figure out 2 power k by 2 in log k time. So this is the overall complexity, and we are not optimizing this because this is well within the time constraint, so this will work. But this entire thing is for an array of size 2. So next we're looking at how to solve it for array of size 3, and then we'll try to generalize it. So I would strongly encourage you to pause and try to look at these two examples only and see if you are able to proceed for an array of size 3 by yourself or not. So again, we have to come up with an algorithm where k is not there, or rather we are not applying operation k number of times one by one. So that's our goal. So let's start with this array, and again this time if you see, if you apply operation here, this would go somewhere here, like in between 3 and 7. So this will be the sorted array. For simplicity, I am now maintaining the sorted version of the array, because it would be otherwise difficult to observe things. But while returning answer, you still need to return the answer in the original order, and for that what you can do, you can simply maintain the indexing of the element with the value itself. So along with 3, you will maintain that okay, 3 was at index 2. Along with 6, you can maintain 1. Basically you got 6 after doing something on index 1, and similarly along with 7 you can maintain index 3. So you can keep maintaining this pair of element instead of one single element. And for simplicity, I am removing this last indexing from now to make it neat, but keep in mind that you are actually, this is not actually at index 2, rather it is at index somewhere, some other index which you need to keep track along with your original array as well. So for now this is 2 1 3, right? Now at this state, what will happen if you multiply here with 3? This would now become 9. So this is now 6 7 9. Now if you multiply this 6 with 3, this will become 18, right? And if you multiply this 7 with 3, this will become 21. If you multiply this 9 with 3, this will become 27. Again, why I am multiplying this 6 7 and 9? Because this is how the ordering would be as well. Like after one operation, this will be the array. After 2 operation, this will be the array. After 3 operation, this will be the array, right? And after this operation, after one more operation, this will become 54. So this will grow somewhere here, and so on and so forth. Now notice one thing again. Will this continue forever? Basically what you are saying is, you applied operation on 6, it become 18. Then you apply operation on 7, it become 21. Then you apply operation on 9, it become 27. Again you applied operation on 6, because you applied you are applying on 18, right? So that was coming from 6. So you are again applying on 6, and then again on 7, and then again on 9. After that you will again apply on 6, 7 and 9. Will this continue forever? If yes, again exact same algorithm, we can divide k equally across these 3 and we'll get our answer. But if this is not possible, then we need to come up with something else. So again, encourage you to pause and try to think yourself. So the answer is yes, this is possible. This will be possible every time. Why? Let's think about it intuitively. This element, let's call it x1, x2 and x3, right? Now what we are saying is m into x1 is greater than x3. That's what we are saying, right? Sorry, not x2, x3, because 6 into 3 is greater than 18, greater than 9, right? Or in other words, 3 into 3 is greater than 9. Like from this point onwards, it would start repeating. So we are saying that 3 into 3 is greater than 9, greater than 7. And if this condition is satisfied, we need to understand that will this always repeat itself? So let's think about it. This is satisfied. So if this is satisfied, then you know that this element would now be after this one. So after one operation, this would be x2, x3 and mx1, right? Now let's apply one more operation here. After you apply one more operation, this will be the smaller one for sure, because this was smaller than, this was greater than x1, but now x1 is greater than x3, so this is the smaller one. So once you apply operation here, this would become x3 mx1 and mx2. Why mx2 is greater than mx1? Because x1 was actually smaller than x2 in the first place, right? So that's why mx1 will always be smaller than mx2. Now at this state, you will again apply operation on x3. So at this state, this will become mx1, mx2 and mx3. Now at this state, you will apply operation on mx1, and if this goes after this, then you know that it will be repeating. So basically what you need to prove is whether m square x1 is greater than mx3 or not. If it is, then I'm sure it will be repeating. And can you prove it from this one? Yes, simply multiply m on both sides, and this is what you will get. So basically, because this inequality is satisfied, if you multiply m, this will go here. In other words, after you apply one more operation, this would become mx2, mx3 and m square x1, right? And if you again apply one more operation here, this would grow after this one, because x1 was anyway smaller than x2, right? So this will continue, and hence if this criteria is satisfied, you are sure that things will repeat one after another, right? Now in this scenario, this criteria is satisfied, and because this is satisfied, we can simply say that we will divide k equally. So whatever k is there, like 1/3 of them will go to this, 1/3 of them will go to this, and 1/3 of them will go to this. And after that, if something is remaining, we will start from here, right? So let's assume that k is 102. 102. Now how will you distribute? You will start with you have done one operation here to get to this state, right? To get to this state, you have done one operation. Again, that question is still remaining, that whether it is possible to get to this state always or not. What we just answered is, if we get to the state, I'm sure that everything will repeat afterwards. But how to get to, whether to get to the state and how much operations will it need to get to the state is something we have to answer again, similar to the two elements array itself. So for now, if we assume that this entire thing is happening, at least for this example, we have done just one operation, so that's negligible. And after that, we have simply divided this k in these three things. So if you divide it equally, this would be like, after you have done one operation already, so you have total 101 operation left. And if you divide this 101 across these three equally, everyone will get 33 operations each. And after that, you will be left with two more operations, right? So you will apply operations in this order. Basically, you will apply one operation here and then one operation here. Now notice that this is not the first index actually. So basically you are saying that 34 operations will go to the second index, 34 operations will go to the first index, and 33 operations will go to the third index. And notice you have already applied one operation in the first index already. So overall, the first index is now getting 35 operations. So at the end of this entire iteration, the value would become 2 multiplied by 3 power 35, 3 multiplied by 3 power 34, and finally 7 multiplied by 3 power 33. So this will be your final state of the array after 102 operations. And again, how to compute this? You can simply use fast exponentiation to compute this entire thing in just log k time. So overall, you just need log k time, assuming this is the state you have reached. If you haven't reached this, we still have to answer two questions. How much time will it take to reach this state? And second, is it actually feasible or not to reach this state or not, right? So again, I would encourage you to pause and try to answer those two questions by yourself. The process is exactly similar. So let's start with the first question, that whether it is possible to reach this state or not, right? Now, what's the state? State is mx1 is greater than x3, right? Now, let's say this is x1, this is x2, and this is x3. So if you do mx1, this time m is 2. So if you do mx1, this would be 4. 4 is not greater than 7. So this inequality is not satisfied, right? So what will you do at this state? You will multiply x1 by m, right? So you will simply multiply this x1 by m, and this will become 2, 4, and 7. Now this will be your new x1, this will be your new x2, and your x3 remains same. So after one operation, what you have done is you have improved your x1, because whatever x2 was there, that was greater than equals to x1, right? Because this entire thing was sorted. So x2 was actually greater than equals to x1. So now your x1 has increased a bit. Either it is same or it is increased, right? So basically, the chances of this inequality being true has now increased. Why? Because x3 is still same, but x1 has slightly increased. So m cross x1 also might have slightly increased, which means this inequality might be satisfied now. But in this scenario, it is not, because it is still 2. So 2 cross 2 is still 4. 4 is not greater than 7. Now, what you will do? You will simply multiply this with m. So again, multiply this with m. This will become 4. Now notice the indexing. Indexing is this 2, 1, 3, right? Now multiply this with 2 again, or m again, and this will become 4. And once you make it 4, this will how the indexing is now. Again, indexing is just now again 1, 2, 3, and this is your new x1, new x2, and new x3. So x3 is still the same, right? Now what you have done is x1 has again either increased or remained same. So in this scenario, x1 has increased. Now if you do 4 into m, this would become 8, and 8 is indeed greater than 7. This inequality is satisfied, which basically means that after this state, everything will repeat. We have just proved that, right? So we are saying that it is always feasible to reach that state. Why? Because if this inequality is not satisfied, it inherently means that you are increasing your x1 after one iteration, right? And because you are increasing your x1 after one iteration, the chances of this inequality being satisfied will also increase. And if you keep on doing these operations, eventually this inequality will be true. And once it is true, afterwards you can simply distribute the operations equally, right? Now, the last question that we need to answer is, how much time will it take in worst case to get to this inequality being true? That I will leave you as an exercise. This is exactly equals to how we proved the previous one. So you can follow the same method, and this will be well within the limits. So next, we will try to solve this entire thing for n elements itself. The approach will exactly be the same. We'll answer two things mainly. Can we achieve a stable ordering? if we can, how much time will it take to retrieve us? Like first thing is like, will this, I think there's one more question which I didn't put, like how much time will it take to achieve the stable ordering. But first thing is, if I reach a stable ordering, can things repeat? Will things repeat? If it is, then can we achieve it? And if we can, how much time will it take to achieve it? Right? These are the three questions. So let's start with the first one. Again, if this is stable ordering, it means if you multiply m here, this would go here. And once you multiply m here, this will go here. And if you multiply m here, this would go here, because x1 was already smaller than x2. Again, if you multiply m here, this would go here. If you multiply m here, this will go here, and so on and so forth. Right? Now, you know that this will occur for one time for sure, because x1, x2, x3, x4, x5, x6 were related to each other. So this will happen one time for sure, no issues about it. But will this happen again? Let's say you did all the operations once. So this becomes mx1, mx2, mx3, mx4, mx5, mx6. If you apply the operations again, will this entire thing, like will this again go afterwards? And if this go afterwards, things will again repeat, right? For sure. So let's look at it. We know that this was a stable order, and because this was a stable order, it means like mx1 was greater than x6. So mx1 was greater than x6, right? Now we did all the operations one. So after 6 operation, this will be mx1, this will be mx2, and so on and so forth, and this will be mx6 finally, right? Now you are applying operations again on this one. So this will be m square x1. Now where this m square x1 will lie will decide whether things will repeat or not. If this lies afterwards, sure, everything will repeat afterwards. So we need to ensure that this is greater than mx6. Is it true? Answer is yes, because this was true, right? You can simply multiply m both sides and this will be the equation you will get. So the answer for first question is yes. If we receive a stable order, in other words, if we receive this inequality, if we able to reach this inequality, things will repeat. Now, second question: can we reach a stable order or not? In other words, given some elements, can we do some operation to reach a stable order or not? Answer is again yes. We can follow the same strategy of the 3 elements array. Basically, if this is not true, what you're doing, you are applying operation on x1, and x1 is now somewhere like beneath this, like it will lie somewhere here. mx1 lies somewhere here, right? It will not cross x6. So if that's the case, basically what you are saying is now the smallest element is x2. In other words, this is your new x1, which in turn means you have increased your x1. And if you do this operation enough number of times, this x1 will be increased to such a value wherein this inequality will be satisfied, right? So hope this entire thing is clear, that we can achieve a stable ordering. Now the final question: how many operations will it take to reach a stable order? I would strongly encourage you to pause and try to think by yourself. I would encourage you to come up with some sample which will help you identify the worst case by yourself. And while you're doing that, ensure that the value of n is 10 power 4. So keep that in mind and try to build your edge case accordingly. So hope you tried it at least once. This is how the edge case would look like. Let's say everything is 1 and last value is 10 power 9, because the maximum value you can have is 10 power 9, right? So what you will do, you will first multiply, this is your x1, right? And mx1 is not greater than x6. x6 is 10 power 9. In this case, this is not x6, this is x 10 power 4, right? So for simplicity, I'm showing it on 6 elements. Now, after you do one operation, this would go somewhere here, right? Now you do one more operation, this would go somewhere after this. Why? Because the index of this is anyways greater than this, so this will go after this too. You apply one more operation, this would go after this one. Apply one more operation, this will go after this one. Apply one more operation, this will go after this one. So after some operation, you will reach this particular state, right? And once you reach this state, you will do the exact same thing. This is your new x1, and this inequality will not be satisfied. So, but x1 has increased. See, previously x1 was 1, but now x1 has increased to 2. So we'll again apply another iteration or another operation, and you will get 4 and reach somewhere here. Again, do that operation, reach somewhere here, and so on and so forth. You will keep on doing this until 2 power 29, because 2 power 29 is still less than 10 power 9. Now you will get 2 power 29 all the way here, right? And after that, once you apply one more operation, things will start falling in place, because this will now become greater than this. So things will start repeating afterwards, right? So how much operation you need to make this happen? So what you're doing is just taking this one element all the way to 10 power 9 takes you log x iteration, where x is the last element itself. So log x iterations, you are able to get this one to a value at which this inequality will be satisfied. But you, like, if there are multiple elements, the minimum would keep changing, right? So to make the minimum the next value itself, you need to apply n number of operations overall. So overall, you will require n log x operations to get to this particular state wherein this inequality is satisfied. So this is the worst number of operations that you are applying. Now, is this better than k? Answer is yes, because n is 10 power 4, k was 10 power 9, lot better. Log x is very small, it will be 30 or something. So 30 into 10 power 4, which is still 3 into 10 power 5, which is still very, very efficient than 10 power 9. Now, notice that once this, so what you're doing is you are applying these many operations in worst case. After applying these many operations, you will reach this particular state, or a state where this inequality is true. After that, you will simply distribute. And after distributing, you will do log k operations in worst case to get this, to find the value of a power v or a power k by n somehow. So the complexity now, like, let's forget about log k for now, because that is very small compared to all of these. So now the major part of the complexity is how to apply these many operations efficiently. So if you apply it naively, that would take you order n square log x time, because you are calculating minimum and then applying the operation, right? So that will take you order n squared log x time. But you can do it efficiently by using a set. So you can maintain this entire thing in a set, and things would, like, you can easily find the minimum value in just log x time, and you can remove it and insert a new one, and the set will still remain sorted. So if you do this using a set, this would be n log x into log n, which is well within the given time constraint. So overall complexity that you have now is n log x into log n plus log k as well, but that's not worth. So this is your overall complexity, and this is something which is efficient enough to pass the given time constraint. So if you have watched this point, would strongly encourage you to pause and try to code this entire thing by yourself. There is nothing extraordinary here. You are simply maintaining a set. I am not showing you pseudocode for this particular set part, because that's just applying the operation efficiently. So you should be able to do that as you're solving this hard problem in first place. Second thing that I have not shown in any of these here is how to do fast power. And fast power, if you don't know about this, you can just copy paste this function. If you know about it, you can write this by yourself as well. So next we're looking at the code, but again, strongly encourage you to code it and get it accepted as well, because at this point, if you're not able to get it accepted, it means something is wrong in your understanding, and you should not proceed forward without at least having a like basic version of the code by yourself, right? So next, looking at the code is exactly what we discussed. We simply, like, we have removed this one from altogether because multiply is 1. So in case it is 1, everything will multiply by 1 and the array would not change itself. So we'll simply return nums. Otherwise, we insert everything in the set because we need, and we insert it with the index as well because we need index at the end, right? After that, we simply apply the operation until some condition is true. So this is final order has that condition. We'll come to that, but until some condition is true, we'll simply apply the operation. What is the operation? Operation is take the smallest element, erase it, and insert it with multiplying by multiplier. That's it, right? You will keep on doing this operation until you have some operations left and your array is not a stable array yet. After you have received a stable array or your operations are exhausted, you can simply distribute everything, the remaining k, across everything. If your operation is already exhausted, this will be 0. So 0 by n would be 0, which will not change anything at all. So after you have divided this entire thing, you will simply compute the first tower because that's the one you will be multiplying with every element there. After that, you can simply iterate over your set, take out element, and see if you need to apply one more operation, because notice that if you simply distribute k by n, k by n, k by 3, k by 3, k by 3 here, the remaining 2 you need to distribute starting from the first one. So that's why we are still iterating from the smallest to the largest, right? So at this state, we'll simply compute whether this will need an extra operation or not. If it is need, we will simply multiply that as well. Otherwise, we'll simply multiply with the val itself, right? And after that, we'll simply put this value at this particular index, right? Now, finally, looking at this is final order. This is like the very straightforward function that we discussed. If the size is 1, we are sure that it is the final state. It is not competing with something else. We need to apply the operation on this itself. To be honest, this was something I do after I got its wrong answers in a test case. After that, you will simply take the first element and the last element and see whether this condition is satisfied or not. If this is satisfied, all good. If it is not, all bad. If it is equal, then you need to make sure that the indexes are matching, like, because what you want is after you multiply m here, this should go all the way back, right? Basically, if you multiply something here, this should beat the final value as well. So let's say this was the index I1 and this was the index I2, and let's say x1 was equals to x6 as well. So in that case, I1 should be greater than I2. That's how it will go all the way back. Otherwise, it will come somewhere between, right? So that's what we are doing. If it is greater than that, then only we will continue. Otherwise, we'll return false. So that's the entire algorithm. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.